Hey everybody, this is a video to help us use StatCrunch to calculate the regression equation of a scatter plot. We're going to do simple linear regression here, and then we're going to learn a little bit more about the Pearson correlation coefficient, or R, that describes the association here and be able to evaluate that. So I've just got a homework problem up here. It's got a scatter plot of salaries. I think this is like television stars, how much they make and how many viewers they get in millions. And we're trying to see if there's an association here between those two things. So the first thing I'm going to do is go ahead and open this in StatCrunch. And here's the raw data. And so we're going to do I want to try to do a linear regression, which it'll do everything we need. So I'm going to go to Stat, Regression, Simple Linear. So just go Stat, Regression, Simple Linear. Our X is their salary, that's the independent, and the dependent would be how many viewers watch, and just hit compute. And we get a little printout here by default that shows us the R value, and the R value is describing the association between the two variables. Now, really positive, if it's a positive number, that means there's a positive trend. If it's negative, it's negative. And this right here is almost zero, which tells me, wow, there's really maybe nothing going on here. Maybe there is no association between salary and viewers. And if I look at the scatter plot, this is peculiar because we've got this one person that's making a huge salary, which really doesn't fit with the other data. But if I, look at this, it's almost flat, the slope. So the R value is kind of describing that slope. If we had a strong positive, it'd be going up. If it's strong negative, it'd be going down. In fact, I'm going to go ahead and show you kind of what is being done here. So I've gone to Wolfram demonstrations, and this is the line of best fit. So what StatCrunch is doing is picking a line that cuts through the data that tries to minimize these boxes. So as I play around with this, you can kind of see, the farther a data point is from the line, the bigger that error, which makes a box which has the same length and width. So these are squares. So the area of these squares is what's being summed. So what we're doing with the best fit line is trying to figure out, what is a line that minimizes the total sum of these squares. You can kind of play around with this with the slope and the y-intercept and try to minimize this, okay? So this looks like it's a positive relationship. It looks pretty strong. This might be an R value of like, I don't know, maybe 0.8 or so. And if I hit show, there it is, the exact one. So that would be the line that minimizes the sum of squares. So this animation is great to kind of visualize what is that line of best fit doing, and what is it trying to minimize actually. So the least squares, it minimizes the area of these squares. If I pick a new data set here, this has a negative association here. So this would be a strong, very strong negative. So this would be an R value around maybe even negative 0.95 or something. Almost every data point is on the line. So very strong relationship here. And so the R value gives us the strength and the direction of that relationship. And then I'll do another data set here. This looks like it's a positive one, so I better switch to positive slope. So this would be an R value, very strong again, maybe like positive even 0.85 or 9 or something. So just want to show you what is actually being computed with that. So now if I go back to, minimize and close that. If I go back to my printout here, so very weak association, but it does gives us an equation that tries to predict what is that line of best fit. It says, it's 6.639 is the y-intercept, and the slope is 0.004, almost zero. So this is again very flat, almost no relationship here. And what we can do now is take a look, and you know what, I'm looking at this graph and I'm saying, this piece of data here is really whacking me out. This is not even close. So what would happen if I actually removed that one? So I'm actually going to try that, and I'm going to go ahead and delete this first data point. Maybe it got mistyped. Maybe it's something that isn't going to help me make a good prediction of this. So I'm going to just redo it again. And regression, simple linear. Again, salaries, viewers, and compute. Now we have an R value of negative 0.735, which tells me, the more they get paid, the fewer viewers I would have. And this R squared value actually is, take that and square it, is 0.54. That describes the percent of the variation that can be explained by this variable. So the percent in variation of viewers can be explained, 54% of that variation can be explained by the salary. So it's definitely, if I'm a TV exec, it's like, boy, this makes no sense to pay people more and actually get fewer viewers. So I'm guessing this data may not be accurate, but let's take a look at there we definitely see a negative trend, but you know what? We've got some dots here that are below, above, above, and below. And I can actually do what we'd call a residual plot. A residual plot would be, and I'll do that as well. But before I do that, I want to evaluate this. This is negative 0.73, sample size of 7. So if I go back to my homework problem here, and it's got a table here. This is the Pearson correlation. So if I have an alpha level of 0.05, which I think is what we had here. Yeah, a significance level 0.05. So I'm going to look in this column, and if I look in row 7, I need an R value, the absolute value of that R value, to be over 0.754 for it to be significant. And notice if it's an alpha level of 0.01, it even has to be closer to 1 or negative 1. So it's the absolute value of that. So it looks like we were close, but when I removed that one, it got us close because we had 0.735 and it needs to be at 0.754. So very close, but still not quite enough to reject the null hypothesis. And that's telling me there's not quite strong enough association between these variables. The one other thing I want to do, I'm going to go into options here. I'm going to go to edit, and if I scroll down, instead of just doing a fitted line plot, I want to do a residual. I want to plot the residuals versus, let's see here. Let's do a residual index plot. That'll be good. And I hit compute. Now if I look at that graph, this actually shows me in that line of best fit. If a dot's above the predicted value, it's up here. And this tells me how far off each one of them is. And we would like to see a pretty random plot here. So if I'm going to pick the next one, if I had added another piece of data, would I be able to predict if it's above or below the line? And I wouldn't probably know if it's above or below. That's good. I want to see randomness, which means maybe a linear model is a good fit. So we can't just look at the data plot. We can't just look at this little printout here and look at the R value or the P value of the slope. And this actually kind of backs up what we just said. See, that P value was 0.0597, and we would only reject if it was less than 0.05. So this actually tells me we're really close, but not quite enough with this data. So we've got the combination of looking at a best line of best fit, kind of showed you what that's doing, gives you the y-intercept and the slope. Analyzing that slope is kind of the R value. It describes, what is the relationship here. It looks like we have a negative, pretty strong, moderately strong, but not strong enough to reject the null and say there is an association here. But this would probably warrant me to do a little more research or get some more data, because when we go and look at the table, the more data you have, the less R needs to be to say there is an association here. But I just want to show you how to use it in StatCrunch. Hopefully that's enough to help you get going in Chapter 10. And, as always, shoot me any questions if you have any.